Okay, welcome everyone to today's session on C++. I'm James Richings. I've been looking in the chat for the last couple of days. So I'm one of the course organizers for this C++ course, along with Nathan. I'm going to be taking the material today. Nathan's going to be around and available to ask any questions in the chat that you might have, along with anything I can grab while I'm speaking. So please let us know if you have any issues or anything you want to ask as we go through this. Just to kick us off, I'm just going to take 5 minutes to review what was covered yesterday, and then talk a little bit about what we're going to cover today. So we focused a lot yesterday talking about resources and how we can manage resources in a way that protects them from being poorly cleaned up and poorly managed, and the different patterns that C++ really allows you to control that. We've also looked a bit at how we can use templating to allow us to reduce code duplication and basically do metaprogramming, having the program generate some of the code effectively itself in a very controlled way. And to kind of cap a lot of this off, towards the end of yesterday, we looked at the multiple ordering example. To do really, this is a capstone kind of part of the course. It's quite a complicated example. It's meant to stretch you a bit. So if you found that challenging, it was meant to. If you found it easy, great. But the point is, it's meant to try and bring again together a lot of elements that you may have only encountered for the first time in the last day or two. So the materials are up there in future. There is a solution I'm going to talk through now briefly, just to make sure everyone's on the same page. But it's not a dependency for the rest of the course. So don't worry, you're not going to miss out on content because that was maybe a bit challenging. Okay, I'm going to look at that in a moment. But before we do that, I'm just going to look forward to what we're going to cover today. So I'm going to do a brief recap of that Norton ordering solution and that example and what we're trying to teach. And then I'm going to talk a little about combining classes. So we talked a lot, I think Nathan talked a lot about classes yesterday, and now we're going to see some of the powerful ways we can use them to make our lives a lot easier and construct complex objects out of them, and also have some warnings around it's very nice in terms of being an interesting feature of a programming language, and it definitely should be used, but overuse can cause a lot of complication, and there are some pitfalls around making your lives sane and maintainable and things like this. So we'll cover that sort of up until the first coffee break around 11. And then throughout the rest of the day, we're going to cover, we've basically got to a level where we're at the top of the abstraction sort of layer. We're kind of quite high up for the rest of the day. And we're now going to use a lot of the fundamentals that's been discussed throughout the last couple of days and see how, by using these tools in standard library functionality or in libraries that are developed by third parties, we can really take advantage of some of the constructs that we've been talking about and how it can make your life very easy and provide you very nice, clean interfaces to do sometimes quite complicated things. So that mainly be covered by looking at algorithms, lambdas, and traits. So we'll be discussing in some detail how we go about using some of those functionality in the standard library. After lunch, we're going to talk about the Eigen library. This is quite a nice high-level algebra library written in C++ that provides lots of common linear algebra functionality in a nicely templated and C++y fashion. So we'll talk a little bit about what the library could offer you and how you might want to use it. And we've got a small example. Just to really, this is just picking something out of the vast array of libraries that exist to show you what this stuff can look like. And finally, to finish the day, we'll talk a little bit about how C++ approaches threading. Now, as many of you will be aware, we're a high-performance computing center, and there's a variety of different ways of doing threading in different approaches. I wouldn't necessarily suggest that this approach is the best approach for high-performance computing at scale type threading, but it is an approach that exists within C++, so we thought we should highlight it here. And we can direct you to many other courses that we provide that look at ways you might want to scale to multi-node or multi-thread in a different way before I make comment on whether things are good or not. Okay, so that's a bit of the plan. So to get us started, I am going to talk about Morton ordering. Has anyone got any questions before I start that off, actually? Okay, well, please do jump in if there's anything that's unclear throughout the day. So I should have reset these terminal windows. 1 second. That's not thing oriented. Just going to increase that a little bit. On the right-hand side, I have the exercise, and on the left, I'm going to have the solution, so we can do a bit of a side-by-side comparison of what's changed in order to enable this. Before we go into this in too much detail, I'm just going to bring up the instructions again to kind of illustrate what we're really trying to get at with this key example. What we're trying to take advantage of is the ability for us to define how we interact with the resource, in this case, some memory. And what we want to do is think about smart ways in which we can access some data location so that if we run through an array of elements, we can make it friendly to how the computer wishes to consume that data. And this Z-like pan here that is a recursive Z-pan is what Morton ordering is basically doing, is that sort of Z ordering is the Morton ordering. And we're going to try and we're effectively trying to finish off a implementation of this in C++, using our ability to access, to define how we do the access interface separate from how the data is stored in the underlying code, underlying memory space, meaning that the interface we use to do the access is very nice and human friendly, but ultimately how the data is accessed for the machine is nice and machine friendly, and separating these two concerns through a dedicated class. Okay, so step one of this example really focuses on, I'm just going to move these around because I'm going to confuse myself if I don't put the solutions on the right-hand side, because I will start by reading the left-hand side the entire time. Okay, so the first thing to say here really is that we have a number of bits that are going to help us here. Geez, my system sounds seem to have returned, which I've been saying. We have some files already that have been done for us that are going to help us out with this particular thing. So we have bits.hpp. So the idea here is that a lot of the detailed twiddling around with where am I moving from, how am I packing, how am I unpacking all this, how am I encoding and decoding data in my special ordering is provided for you. Okay, so there is an encoding and a decode functionality for you, which deals with the fact that I've got to move certain indices around. So you should be taking advantage of this. So this is highlighted a little bit in the text, but if you hadn't noticed this, you don't have to worry about figuring out how you should be doing the bit twiddling. That is provided. So we'll just go into step one and look at what we're asked to do. So yeah, we've got a 2D square matrix that stores data in the Morton order. We require the size be a power of 2, so everything's always square. The matrix could be a fixed size, so we don't have to worry about resizing it, which could change all the ordering dynamically, which would make things complicated. And we're setting some constraints. So we don't want this matrix to be copyable. So there's an assumption here that we're doing this ordering type construct because we've got a very large matrix, and we want to make that once set it up in an efficient way and then never touch it during the lifetime of our program, so we don't duplicate a large amount of data. So we can decide that when we define how this particular class operates, that we're going to restrict what it is allowed to do, which is sensible. So we can restrict copy the ability to copy it. And it must use, and we're also saying we must use an explicit duplicate member function instead. Okay. To start us off, so we've got a number of to-dos we need to go through. So we'll just go through these, then we'll look at some of the solutions. So do we need to do anything around how we define our matrix based on our different constructors? So if we've got a default constructor, what should we do? Is that enough? If we've got a constructor which is takes a value, what do we need to do here in order to allocate the initial memory for this? Which functions do we need to delete and set to be default in order to deal with our constraint around ability to copy this matrix? So implicit copying is not allowed. We've already got the deletes in there. That's good. Okay, so that's dealing with our copyability, but will the default implementation for move be okay for what we've required? So we have to think about that a little bit. We need to consider what happens on destruction of this matrix. We had a statement that we need to have an explicit duplicate command. So we don't want to use the sort of implicit underlying functionality of C++. We want to make the programmer do something explicit. So by having a new function that we've defined ourselves, we need to add that functionality in. We need to think about element access, how we're going to do that. So we should consider how we're going to use those encode and decode functionality around here. Similarly for raw data access, how might we do that? And finally, we need to think very carefully about how we're going to choose to store the data and manage the memory that we store. So these are the data members. Okay. So actually, I often think that making this decision first is the most helpful. Okay. So let's just look at that initially. So we need something that means that we are never able to copy the data that we are storing, so we never duplicate it. So a standard unique pointer is that requirement met. So we want some array of elements of some unknown type, because we don't want to say this is a modern ordering of a particular data type. So this could be int, this could be an int array, this is just a sub or a char array or something, but this is an array of some type. And we're saying it's going to be a unique pointer of this, and that's going to be stored at this base data, variable data, which means that the underlying data cannot be copied within our setup, which is exactly the requirement we had. Okay. So now we have that, we can think about the other to-dos on our list. So let's just head back to the top. So our first item to think about is there anything to do around the sort of default initialization? So we're setting the rank to 0 because we've got no elements, but a unique pointer, we don't have to explicitly set anything for this unique pointer that's holding our data, because it has a sensible default initialization itself. So we don't have to do anything there explicitly. However, when we want to set up the matrix and we provide it a particular rank, we do now need to size that size the unique pointer to a specific array length. So it's a square matrix, so it's going to be whatever the dimension is squared in order to get the correct size. So we have to, in the initialize of this, to add that our data is going to have this size. Sorry, I'm just seeing these questions right. I tried to use standard a vector for data. So Jack asked, I had tried to use vector for data. Is it preferable to use an array because we know the size in advance? I suspect the array might be easier to work with down the line. What we're trying to do specifically, so data is a array wrapped in a unique pointer. So you do know fixed length in advance, so you can just allocate it. You don't need the dynamic properties of vector in the requirements of this matrix. So we don't need all the additional functionality of vector effectively. Okay, can you please say again why we need a unique pointer in this example? So we don't want this to be, we don't want to duplicate. We don't want this thing to be copyable, right? We want this to be a unique item of data. Imagine this is 10 gigabytes. This matrix is humongous. Okay, 100 gigabytes. My node only has 110 gigabytes. I can never have this be copied. So I'm trying to define some type of our matrix, which has this property. So the underlying data source, if we make it a unique pointer to something, it can never be copied by construction. That makes our life meets our requirements. And instead of us coming up and deleting certain we shouldn't try and which we're trying to do separation of concerns here, where we're separating the data storage from the functionality that we want. The copyability of the data we're trying to hold on to can be set a unique pointer. We shouldn't try and build some Franken class which does exactly the same thing as a unique pointer, but just doesn't use the standard library functionality. We should just use that. That's what I'm trying to get to, really. Okay. So just going down our list of the other parts of this example. So the implicit copy was explicitly deleted already. I just want to highlight this out again, that we deleted copy construction and we deleted copy assignment. So that means that the matrix can't be copied, not the underlying data that's stored. That's dealt with the unique pointer piece. And then moving is allowed. We're allowed to move data, so because that doesn't cause us to copy it. So we're happy for the matrix to keep its default movement operations. So this is also because default is okay because we choose unique pointer to manage the data storage. Unique pointer has sensible ways of doing the data movement and meets our criteria. They won't copy anything under the hood. Therefore, we're okay to do this. Okay. So we're really kind of mirroring some of the functionality unique pointer, because by doing default here, what we're saying is compiler, go figure it out. And what that means for the compiler, it goes down to the data members, which are right at the bottom, goes, right, can you work out how to do this yourself? Yes, I can. Okay, do it. Can I work out how to do movement for this? Yes, I know how to do it for unique pointer, and this is just an array. That's easy. I can figure that out. The danger is if you don't, if we just left the compiler to deal with this on its own, and we hadn't made that a unique pointer, and we'd sort of not deleted these, for example, it would figure out how to do the copies under the hood, and then you wouldn't have the restriction on how whether you can copy data that you require for this particular example. So as I said earlier, this is quite in depth, but what this is trying to do is pull together a lot of the concepts we've discussed in a case where there's a genuine reason why you wouldn't want to copy or move something. So just imagine this matrix is very, very large. Okay, so we need to think next about our destructor and what we need for this. So again, we could just use default. The unique pointer has a destructor which will do something sensible. It will delete any matrix, any data that it holds. That's what we want. It will clean up that large array that we've passed it, and the rest of what we have is just a integer for the rank. So that will get deleted correctly as well. So what we have said is that we can have explicit duplication. So what we're effectively doing is having the ability to copy, but we're not letting it be held by the standard functionality of classes, so that the compiler can never do anything fancy and interpret how to do copy on its own and put it in places which would give us a risk of overloading memory that's available on a particular system. But we still want to provide the people who use our matrix class the ability to copy. Maybe they haven't got a massive matrix, maybe they've got a small one, but we're going to force them to actually explicitly write, I am making a duplicate in their code so they know what they're doing. And to do that, we can use standard copy underneath this and access the data to copy it. Okay. So we make a new matrix object and we construct it with the rank that's of this matrix. It's a little bit cyclical. We're referring to ourselves, but there's a new instance of this being created called answer here. And it takes the rank that we currently hold. We copy all the data from the start to the data plus the size, and we put this into the answer, and we return that. So when it's returned, there will be a fresh duplication of this particular instance of the matrix. So we have some getters for rank and getters for size that are already provided, so we don't need to do anything that. So that's where size is coming from. We then need to think a little bit about access. So we want some constant element access and we want some mutable element access. So we've got say constant of type T, and we're going to use an operator rounded brackets, sort of standard brackets, in order to do this element access. This makes it a bit more explicit than using square brackets that might seem like some default access confuse people. So you can pick your brackets to make it a little bit more explicit about what you're doing for people. We then we need to provide two elements in order to access a particular element of the matrix. We're then going to use this encode function that says, based on the ith and jth element of the matrix, if I just look at it as like a chessboard, I'm going to encode that and get the exact element in my actually just flat array underneath the data storage. And that encode deals with all the bit twiddling, so the access pattern meets the I said pattern that we're trying to enable. And that allows us to set the access quite nicely if I'm just accessing data. Similarly, we have a mutable version, so we've dropped the constants. It's basically say we're returning something that's constant and we're not going to edit it. Here we say, no, we make no claims of that. What's returned, we may well edit that location. So beware that we may do that if we choose to. And then separately, we've got raw data access, where we've got a data where we can go after the particular elements. So here we're going to use the getter to get at this, and this is the get function, which is in the unique pointer. So here we have again a constant and a mutable version of it, and we're just accessing directly on here. So we bypass all our encoding. Okay. That was step one. That produces us an example of a matrix which has the properties that enable us to access through modern ordering. Step two then says, well, that's nice and all, but I don't really want to access it by functions. I'd really like to use a lot of the standard sort of C++ kind of interfaces and looping arrangements that exist. I don't know. It feels a bit C-like to just get data. So what if we do something extra? Yes, right. So now we're going to consider whether we can produce an iterator. So say we now want to have a matrix iterator that allows us to do this data access and then enable a lot of the C++ functionality in the different ways we can use loops over containers in C++ in order to do this access. So we're going to have our standard matrix class again, and some things have been provided for us. So the left, again, remember, is the example before it's been edited. To the right, it's got the edits. So I will call out the to-dos again and highlight what things have changed. We now specify an iterator and a constant iterator. So we're going to have two new classes. And we're going to provide some functionality to access the matrix with these particular iterators. Okay. A lot of what's in here hasn't actually changed. It doesn't require change. What we're mainly going to focus on is the additional functionality we have at the bottom here. So we need to provide a begin and end function if we want to provide an interface to this matrix, this container, which is matrix is a container that holds data that allows us to iterate through it, and we need to provide a begin and end for the mutable case and the constant case. We've kept all the other access mechanisms we already have, right? We're not changing. We're just requiring some additional ones to do this. There's no new data members either. Okay. What else are we going to need? So we're going to need a matrix iterator to do this. So we, at the top of our matrix class, we said we were going to define some type names, really, that by specifying the using command. But matrix iterator needs to be defined somewhere, so we need to also define that, and the stub for that has been provided for us below. Okay, and this is where a lot of the work we need to think about needs to go in here. So we have a class called matrix iterator. It inherits from the standard iterator class. So basically, what we're saying is we just need to provide the functionality that is required in the standard iterator and make sure that our matrix iterator has this all in, and provide the access that we need in order to make sure all the operations required by an iterator are set up correctly in this case. And that's a lot of exercise too. We need to find some data members as well. Okay, so let's just go through that. So I'll skip over the things and come back to them. But effectively, what do we need to do? So we've got a default constructor that we may need to think about editing. So we must provide copy constructor and copy assignment. We need to get particular coordinates of the current element. We need to provide the equivalence operation. We need to provide the not equals operation. And then we also need to provide, this is kind of done for us. Okay, this is not the equivalence operator. It's a bit cheeky. So this will get done for us if we've got this done. We need to provide a dereferencing operation. We need to provide incrementation and decrementation as well, so that we can move through the iterator forward and backwards. And we need to find some data. So let's start at the top. So we need to think about our constructor. So what do we need? Sorry, let me do that wrong. Let's start back down here. What do we need for data? What do we need to store in order to enable this? For an iterator, we need a start position and a current position. We need to say where the beginning of our iterator is and where we are right now. So we need to define those. We're going to use an underscore start and underscore point. And that allows us to say where we begin our data and where we've got to. And then we've got all the operations to move through this. That means when we set up our constructor, we need to set these to nodes. So these are pointers to these locations, the beginning and the current location within our container. we need to provide that was going to set them as null pointers. So by default, it's going to construct something that's kind of harmless. In order to enable us to tick up, to be able to use all the other elements here. If we want to get the particular XY coordinates, so like the chessboard coordinate of this, we can then just work out our location by picking the relative, to get our position through the array. It's just the difference of these two. It's the starting, this is like the offset from the beginning of the array, is effectively the distance between start and the current pointer. That gives it Z, and we can work out what X is by using our pack functionality that we have in that bits CPP file. Similarly, to get Y, we can do the same thing. Okay, we're just having to do a bit of bit shifting in order to get the relative position. In order then to check if the equivalence operator is set correctly, we have to check whether for a particular matrix iterator, the pointers are equivalent. Okay. That checks whether the iterators are equivalent. As I said earlier, we're using the not of that result in order to do the not equals to comparison. If we want to dereference our particular iterator, well, we're just dereferencing the underlying pointer of the iterator, so we can do that pretty directly. Similarly, if we want to do incrementation, we just increment the pointer. And then we return this whole current class, its current state, because we're updating the state of the class, of the instance of the class, sorry, my language right, we're updating the instance of the class, and then we are returning that. The same with the incrementation, okay? We then have the same process. Okay. So that's all we need in this matrix iterator, and that's relatively simple. Okay, there's no crazy class function that's really going on here. There's nothing horribly templated about this. It's just pointers. So the final thing we need to think about is how this interacts with the matrix class itself, because how do we actually use this? So we need to provide the begin and end functions that C++ wants as the interface in order to enable many of the nice looping constructs that we have in C++. But we can do that just by providing to data as this raw access, and it just tells us where we are. So if we're at the beginning of the iterator, we're at the beginning of data, so that's just data, and we're at the for the beginning, both of these pointers are, the start point is always set to the start, and the pointer is then set to the start. That's the beginning of anything. And then in the end, it's data plus size. So we've got begin and end available here in order to set the pointer to be whatever the size of this is currently. And similarly, we have the same for the constant versions of these. So what this then means is that we can use these two, the begin and end, and then be able to increment through the data using the functionalities of the matrix iterator to be able to use range-based for loops, to use iterator for loops, type constructs, the stuff we like to use in C++ because it's all very clean and range-based on containers. And we've done that from scratch in our own container. So this example is quite complex, but it does pull together several of the same lots of elements together into a single place. And what it really tries to say is that the nice thing that C++ allows you is you're not constrained by the containers defined within the standard library. You have the ability to create your own. Are there smart choices and bad choices about that? Of course, in anything. But it does allow you that power to do that sort of generation of your own structures. Okay. Quick questions. Yeah, good point, Nathan. So we can use the raw pointers in matrix iterator without implementing the copy and move constructors. So that's a good point I missed jumped over that a little bit. We don't actually provide any of these copy move constructors because they don't own the data. They just provide a view on the data that the unique pointer owns in matrix. So we don't need to worry about how the data. We don't own the data in the iterator, so there's no risk of us copying that by default. So we haven't had to explicitly delete things in the iterator class. The matrix class is exactly the same as it was in this solution. We've still deleted explicitly copying here because the matrix class owns the data inside unique pointer. Yeah. The iterator just provides us a view on this. Okay, so we'll have some time towards the end of the day to look at this exercise again. If people haven't had a chance to go through this in detail or want to discuss it more, I'm happy to take questions. Please remember also to use the Collaborate session, which I have forgotten to publish the link in the chat again this morning. If you have questions that you think are going to get lost in this stream of chat, we'll try to get back to them as and when. Okay, I'm going to now move on because I worry we will run out of time if we don't start the next section. Okay. So we've talked a lot about resource management and classes. What we haven't discussed is how we can really combine them together. Now, we saw a slight example of this in that exercise, where the matrix iterator inherited something from the standard iterator environment. We are desperately trying to remove this slight ordering dependency in this course, but it's very difficult to take it all out, so that we're not introducing topics before we've actually taught you about them. But that one was kind of done for you. But we're going to now talk more explicitly about the ways we can combine these classes in order to reduce functionality duplication and make your lives a bit easier, and then also think about how it can make your lives terribly, terribly harder if you don't think about this very carefully. Okay. So yeah, we discussed how to create new object types for classes, how to edit their properties of these classes around sort of creation, destruction, copying, and movement. And then in the example, we've seen the ways to build containers with classes with a specific purpose. And we've seen how templates can make these classes be used in a generic way. And now we need to think about ways we can do combinations of these classes. So we have inheritance. It's the simplest case. We have multi-level inheritance. So we have more than one layer of inheritance. Multiple inheritance, which is a class taking information from two other classes. We need to then think very carefully about access specifiers. And then we will discuss a bit about polymorphism and the ability to swap functionality then out in different ways. Okay. So what is inheritance? In C++, it's possible to inherit methods and attributes from other classes. There are two types of classes we'll talk about when we're talking about inheritance. Derived classes, or child classes, classes that inherit information from another. Base classes or parent classes, classes that are inherited from. If this is confusing, don't worry. We will do lots and lots of examples that look like what you see in front, where we will have classes explicitly called parent and child. There is no need for them to be called parent and child. This is entirely a way to try and illustrate this. We will have effectively grandparents and cousins in lots of cases as well, in the examples we show. So here, in this block of code, we have class parent, which has a public section, which has got a public constructor and a public data member A. And then we have the child, which itself has a public constructor child, which is set to its default, and it owns an integer B. It is also doing inheritance. Okay, this colon and then the name of another class means that the child inherits everything from parent. What it means is, in practice, child actually has an integer A and an integer B as its data members because it's inherited it from the parent. So what does this look like? I thought we had a little example here. Okay. What we do need to think about is very carefully, though, in the above, everything is public. But we may want to control access. So here, int A is inherently public, so anyone could access this really from parent anyway. And here it's also going to be public, so anyone could access it through the child copy of it as well, if it's got both. Same way as that anyone could publicly access B, the child. But to kind of prove this is doing something a bit more interesting, we have this, we have maybe that the constructor is public, and then we have protected our integer A within parent. And we've given it some default value. We've said it's 1 now, give it something we can seek about. And what we've done here is we've made our child class a little bit more complicated. We've said it's got public constructor, and we've got some public print function. And just to prove that we've got some interesting output happening, we've got A being printed and B being printed. And we're trying to prove to you here that it can access the data member that's set in parent and even the value that was set inside this parent through inheritance. And we've now got a private data member of child. A child is the only class that can see this private data member. So if we just look at this example at the bottom, so if I have a new program which has got a child X, a instance of the child class called X, and we call print on it, it's going to print both A and B correctly. And that's because child can see the element A is equal to 1. And what this is doing is basically saying, well, we're using the correct specifier for this. Public means the members are accessible from the outside of the class. Okay. Private, members cannot be accessed or viewed from outside the class. Protected means members cannot be accessed from outside the class. However, they can be accessed in inherited classes. So child is inheriting from parent. It inherits A1 and is allowed to see it because A is set by protected. So we can also specify the level of access we want when we inherit the parent class to the child class. So I can add an access specifier here that says, parent, you have a public integer A1, a protected integer A2, and a private integer A3. That's what you've decided that you're allowing access to. But when I choose to accept everything from you, parent class, is effectively what this specifier determines. So this public keyword here makes the public members of the base class public in the derived class. And the protected members of the base class remain protected in the derived class. Okay. Protected inheritance makes the public and protected members of the base class protected in the derived class. So by adding protected here, this means that int A1 is actually now protected within child, and int A2 is now protected is still protected within child as well. Okay. So by heading private here, it makes the public and protected members of the base class private and the derived class. So now A1 and A2 are private within child. So this allows you to specify and control what you choose to accept in the derived class, in the child class, which can be useful if you want to set more levels or more fine control. So those are some points on one layer of inheritance. If we then think about having multi-level inheritance, I can continue this argument. So I now have a grandparent effectively. It's you won't hear people generally talk about things being grandparent classes. That's not sort of something in the terminology that in the field really, or sorry, in the development. I just think this is a better way of explaining this concept to people to understand what the generation thinks. So this is really our starting point, our base class. It has a public constructor, which is just default, and it has a protected integer A. I can then have a parent, which is inheriting from the grandparent. It has a default constructor that's public, and it has a protected integer B. The inheritance is public. I then have a child, which inherits from parent. The inheritance is public, and it has an integer that is private, C3. Again, we have a little print functionality that allows us to print everything that's public, and we have our constructor, which is public. So I should be able to print all three of these because I have inherited through everything that was protected came in as protected further down. So this has now got a protected A and a protected B. So therefore, when child inherits it publicly, it gets a protected A and a protected B. Okay. And I can print this, and therefore my child, because that's all I've done, I've not changed this example at all. My child is still just calling a print function, but now has 3 things it prints. So if we just go back 1 second, compare that to the previous example a minute ago, see that this is the same call. It's just a child X and X call on print, and it printed 2 things because this had 2 levels. If I go to the later example, I've got 3 levels to print, and I call exactly the same. I create a child, an instance of a child class, and I print on it, and I print 3 things. This is an incredibly naive way of doing this. I am setting the values of A, B, and C explicitly in the classes to make this simple. You can do lots of very complicated things with this. This is one of the areas where we say sort of danger, beware. If you can do turtles all the way down, so you can have lots and lots of levels of inheritance and make this horrendously complex. Very big danger here is that you don't end up with a file that you as a human reads and that says, these are all the elements in this class, even though you've done a bunch of inheritance. It's not like they end up in there. So it's hard to know whether you could explicitly see what everything that ends up in child actually is. Because you have to actually look at 3 classes to understand what ends up in this child class. So you have to look at grandparent and parent explicitly to understand what's really in here. That saves code duplication, which is great, but it increases the complexity of the program significantly. So you need to think very carefully about how complex these structures can become. Okay. Oh, now you've gone and got me. I think it's public, but Nathan's going to jump in the chat and tell me I'm entirely wrong. I will look it up in a minute. Yeah, I think it's public as well. Okay, good. So the interesting way to test that is that you effectively do this example here, and you change this. So this is, I'm not specifying explicitly what the inheritance type is. If you change where you set the data member to, and it has no effect until you hit private, then it's that. So the default for private for classes and default for public for structs, that's the this specifier in here, which is the structures within the class. We're talking about there being no access specifier here when we do inheritance. If it defaults to the default for classes, it would make some sense. But then what it means is that if you do inheritance, you lock everything down very tightly, and you don't get any of the benefits of inheritance necessarily. So I think public is probably more likely. Yeah, it's fine. It's a. Oh, you think that is right? Ah, okay. See, I'm wrong here. The point is I'm sorry. I know this is probably confusing some people here. It's not my intention. The point I'm trying to make here is that a lot of these times that we have to go double check these because the way to do that check, and you end up writing is these little example codes. This is what the little test is, and you try some stuff out because the standard will tell you something, and you go and confirm it, or compiler version's changed or something, and you're going, well, actually, it'd be better to stop just actually running an instance of this and confirming. So don't be afraid to ask these sort of very sensible questions and go to check this out yourselves. Okay. All right. Okay. Let's move on. So we've talked about multi-level. We've got the concept of 3 levels inheriting all the way down, and this can be extended further, but be aware that there's complexity here that you should be very careful of. The second thing we have is multiple inheritance, where we're inheriting from multiple sources. So I inherit from parent A. It's going to set some protected value A, and parent B is going to set some protected value B. Again, we're doing exactly the same structure for our little parent classes. They have nothing special or interesting about them whatsoever. I then, in my child, and the special thing I'm doing here is I've got a list of classes I'm inheriting, public A and public B. And by doing this, I have information. And once again, my child class has its little in C that it's private, and we print all 3 of them. Okay. Again, this code has not changed. Fundamentally, this is exactly the same test program I've run every single time we've changed the way we do inheritance. I have not changed this once. What I print has changed. Okay, I could have done smarter thing about the examples. It wasn't A, B, and C. The only thing I tried to be clever is I've changed the value, so it's not looking like multi-level inheritance. It's multiple inheritance, and the values that I provided are slightly different. But the point is, parent A and parent B sit on the same level of the inheritance tree, and they're not. This is not passed through like we had in the previous example. But I still get the same. I can still run. I can run the same function, but get different functionality effectively. Again, be very careful. You can have very complicated inheritance structures here. One specific one, which is a big problem, and you need to be very careful of, is diamond problem. If I inherit, so far what we've really looked at is this kind of bottom part of the diamond, so triangle. Parent 1 and parent 2, parent A, parent B, both inherited by the child. That's okay. But if they then have a common ancestor, there is a risk that they all do this. They have the same functionality being brought to child from 2 locations. So here's the example for that. I now have base class. Okay, it's got some function saying I'm the base class. Nothing special here. I'm making these two classes incredibly minimal for space saving reasons, but basically what I'm doing here is I'm saying all you've got is a constructor. That's it. Just being, I should probably delete public, but I kind of want to say that there's a body here. It's going to have a default constructor. It's going to figure that out for itself. So parent A just constructs itself, but it's inheriting from base. So it inherits this function. Parent B also has some default constructor, and it also inherits from base, which means it also has function. Child then inherits from probably from parent A and parent B. And in the main function that we call, now I've changed it slightly, I have a new child object, and I'm going to call function. What do people think will happen? Put your answers in the chat. Okay, yes. Yeah, it's going to complain at us. Okay. So it doesn't know how to, at compilation, know which one to choose. So therefore, we have an ambiguity that arises because there's two copy of functions that you could use from. And there is a fundamental issue with this that we need to be very careful about fixing. Okay. Sorry, so I think I'll come back to that combinator in a minute, just to not jump back and forth too much. So what we can do is introduce a concept of virtual here. So we can have this keyword that we're going to inherit from a virtual copy of the public base class and a virtual copy here. This we're doing, therefore, inheritance is virtual inheritance. So therefore, there is no ambiguity anymore about what this function is. So we need to use the virtual keyword here to do this inheritance instead. Okay. So we'll come back onto that in a minute in more detail, but we're just going to consider another question first. So far, when we've looked at this example, we've had you always use default constructors. And now if we explicitly write a definite constructor, so I'm going to have some at the end, something stupid is just to make the compiler not run over what we're doing and come up with its own ideas. I have explicit statement here for parent A and for parent B. They've just got exactly the same thing apart from their name is explicit inside the print statement. When I call the constructor, I need to, if I call the parent A and parent B here on construction of the child, I will also get some, also call the constructors of the parent A and parent B. So I can split off the construction information of some maybe I want to, instead of setting A and B equal to 1 or 2 or whatever in there, I can have it explicitly done in the constructor. And then you can imagine that I can do something far more complicated than that constructor than just setting value to an integer. I don't need to duplicate that functionality in the child. So here, for example, I'm not even doing a call to print or anything here. I'm just making a child object. And I still call, and simply by adding these lines into the child's constructor, onto the initializer list, I then call the constructors for parent A and parent B, and then I call the constructor for the child. Order of construction matches order of inheritance. That's the key point here. So if you have some order dependency, you just need to be aware of that. Okay. Similarly, we need to think a little bit about destruction. So again, here I'm going to call define an explicit destructor. Up until now, I've just let the compiler handle this itself. Again, I'm not doing anything fancy. There's names separately for parent A and parent B, and I've got multiple inheritance here. And now I just call the child destructor. The destructor is called when we reach the end of its scope, and the destructors are called in reverse order of inheritance. So I don't need to explicitly add these in here. This will be called the end of the scope. Okay. So this is where we're now trying to deal with some of the consequences of inheritance on the construction and destruction of a particular class. Okay. So polymorphism. So what if we want to overload certain operations in derived classes? We might not want to inherit all the functionality. We might want to change some of the functionality of the class we've inherited from. So given a parent class, and I'm back to just giving a default constructor to make things a little bit quieter for us, I might have a print function that just says, well, from printing for myself, I just need to print A. That's what I'm doing. I'm explicitly adding in that this print has come from the parent class, and I'm just going to print this value. I then have a child class, which is inherits from parent. And it's going to have a different print function. This is going to be called print output from child to make it explicit, and it's going to print A and it's going to print B. Okay, there's a private B inside child. So I'm going to have a simple test for this, where if I create a child, the instance of this child is called X, and I print from that, I call the print from the child. If I have a parent called this instance called Y, and I print from Y, I just call the print from the parent. Okay, so even though the child has inherited this functionality, print, it has overridden it in its own definition. So you can redefine functionality in derived classes. I could have done something clever and cool from print from the previous one, things like this, but I haven't. But the point here is you have the ability to do this. And this can be very powerful as well. If you start thinking about combinations where you don't want to match the exact same functionality, then you can then add additional functionality in sort of a nicely, you can nicely wrap functionality that already exists. You don't duplicate code. You can add your own changes, and you don't have to just take everything you're given by the class you're inheriting from. Okay, so I said we come back to the sort of virtualization. So specifically here, we're going to talk about, before we were talking about a virtual inheritance, and here we're going to talk about virtual functions. So when is the decision made about which print to use? Because we could do this at different times. Is it happened at sort of compile time, or is it happening at runtime? If we take this example here, I can have a base class with two functions. I'm going to have one that's called print, which is going to be virtual. And it's just going to say print the base class. And we're going to have something called show, which is not virtual. And we're just going to show the base class. We're going to print out, show the base class to us. So the key thing here now is that print is virtual and show is not. Similarly, I'm going to have some derived class. This is our child class. It's going to inherit from base. It's going to have its own print derived class, it's going to say, and it's going to have its own show derived class. Print in the derived class is not virtual. It's the only virtual place is going to be in this base class. So, and this little trick's a bit complicated, but effectively what I'm doing is I'm going to have a pointer to a base class called bPointer. I'm going to have an instance of the derived class called D. And I'm going to say, well, base class pointer, you're going to point to that particular instance of B. At no point here have I explicitly created a version of the base class, an instance of the base class inside my main function. Okay, all that's happening is there's a base class pointer which is pointing at this derived class. So, and then we're going to call through the base pointer print and show. Okay. What we're going to see is, sorry, I've realized the results on the other page. We're doing exactly the same thing. Base pointer, only instance of a class is actually a derived class, and then we're just pointing at from the base pointer. If I call through the base pointer print, this virtual function is potentially bound at runtime, and therefore we print the derived class. If we do show, it's bound at compile time, and the show is the base class. Got a base class pointer, is expecting to show the base. It's not going to do the replacement. It's done that at compile time. So this virtual function can get overridden by this version of the function in the derived class at runtime. This allows you to choose when you switch out functionality at compile time or runtime through your classes. And that is, again, immensely powerful. Okay. There's obviously some risks around doing this sort of thing. So we can have a case where we want something to be overridden, and we want to have a check. We want the compiler to check for us that it has actually been overridden. So say we have this virtual void function, it's in the base, and I have a derived class void function. If I did something silly by putting in an int argument here, see how the signature of these don't match? This does not match this. So these are not going to override each other by default because they are different functions with different signatures. So the compiler isn't going to override one with the other. I could put explicitly the keyword override to tell the compiler, I'm expecting this to replace something. If this doesn't replace something, throw me an error because there's something wrong here. Don't have an example for this, but you get the point here. There's a keyword that's effectively allowing protection so that we don't generate additional functionality. At no point is int a used. This is entirely a program error. But if you get this to be very, very complicated and you're dealing with multiple inheritance and then virtualization across many files, you want to be very careful to say, do I expect this to override something that's already existed in a base class? You can then tell the compiler to help you out with this by using keyword override. Okay. So there's lots of different types of polymorphism. The main two ways we can think about this is we have it at compile time where we do function overloading or operator overloading. Or we could do this at runtime through virtual functions. Okay, so there's a question. Would it be sensible to make all base class functions virtual and explicitly overriding children to avoid diamond issues, etc.? I think there is a cost for doing this because you then create a lookup that has to be called at runtime to deconflict, and that's potentially a performance impact. I would have to double check the exact reason for that, but no, you should not by default. Yeah, there's a performance impact for virtual functions. So it's not something you should do by default, but it is there if you want to take advantage of it. If you're moving something, I think this diagram is really valuable. If you're moving it to runtime, then there is a performance implication for this. Is it very large? Depends on what you're doing and how complex your inheritance structures are. Obviously, it's going to have to do far more work if there's a lot more deconflicting to do. Okay. Right. We now have time for an exercise. I have classically run over slightly in terms of my time for this and how much time I wanted for the exercise, I believe. Just going to check I am not completely bereft of our timings. Okay, so we plan to have a coffee break in 15 minutes. Let's still aim to do that, but we'll give ourselves a little bit more time to do the exercise after that as well. The exercise is actually, let's just find it here. Okay. The inheritance exercise has been updated recently, and it basically gets you to try and do some of these examples of multi-inheritance, inheritance and multiple inheritance, and get you some experience with this. It's exercise number 7 within the files you've downloaded. It contains 3 subdirectories, part 1, 2, and 3. The include subdirectory contains 2 files, vector HPP and vertex HPP. These contain a pre-made sort of vector and vertex class you'll need for the exercise. You don't need to modify those files. What you're aiming to do in part 1 is look at multi-level inheritance. So again, go through the to-do items in that example and have a go. Part 2, we'll look at multiple inheritance. So there's multiple classes you're bringing together. And part 3, looking at virtual functions. Go through the examples one by one and see what you have. If you have any questions, please let us know. And let us know what you think and if that makes sense as you work through them. So as I said, we'll have 10 minutes looking at this now. We'll take a coffee break at 11, and then we will spend probably another 20 minutes after that looking at this as well.
Just in the interest of time, I think we'll start going through this exercise, and then James can get on with the next section of content. I'll just set up my screen share. That one, I think. Cool. Okay. Yeah, we'll go through this. Each of the parts. Part 1 and 2 are somewhat involved, so kind of know. Whereas if you haven't quite got through them, that's okay. Cool. I think the place we'll start here is probably this element.hpp file. So you've been provided with this kind of base elements class, which provides has a vector of vertices, and then various member functions to kind of get the number of vertices, get the number of dimensions, and return this vector. And the intention is these number of vertices and these number of dimensions, some other child classes will kind of override them and change what they do. So the first to do we've got is to add some access specifiers to this class. So what we're going to do is we're going to make the first section protected. So we've got our vector is going to be protected and our constructor is going to be protected. And what that means is that you cannot create an instance of element, but classes that inherit from the element class can still call the constructor. So that's going to be protected. And then the rest of it can just be public, because these are just public member functions that we're going to use. So that's kind of all we need to do there. So then we can start looking at our next classes up. So we've got element 2D and element 3D, which are both going to inherit from element. So the first thing we can do is add that inheritance. So we want to do public inheritance because we want to have all the kind of functions that define an element, we want them to be publicly accessible, kind of keep the same accesses that they've already got on them. Next, we want to add any necessary constructors. So again, these can be protected, and because again, we don't want to necessarily create an instance of element 2D itself. And again, we're going to take in a vector of vertices. And what we're going to do with that is we're going to call our element constructor. Because that just takes in that vector and does the kind of initialization for us. So it's just this colon, then calling the constructor of element. And then for our 3D element, it's exactly the same. So we'll just copy that over here and change the name of it. Just add our protected specifier. And then the rest of our class can just be public. So we can just add that in here. So next we want to override the get number of dimensions method. So the function of this is it's returning an integer. Getting the number of dimensions, it's a const function. And for our 2D element, we're just going to return 2. So the 2D element has got 2 dimensions. And then for our 3D element, again, we just return 3. So next, in our 2D elements, we want to be able to compute the area. So this is kind of a standard interface we want for our 2D elements. So it's going to just return a double called area. Again, it's constant. We're not changing anything about the element itself. And for now, we're just going to say return 0 because any child classes can override this for how you calculate the area for their type. That was a question. So we probably should use the override keyword in general, yes. This poem didn't have you do it, so part 3 started looking at virtual functions because I believe, can I just add override to this one? Oh, sorry, we're not. So here we're not overriding a function here. So num dims, you're right, should probably have the override keyword, except then it will right, base class member. Why is that complaining at me? I will leave that in for now. I seem to remember, I think, does override have to be on a virtual function? I think it does. And I haven't currently defined these to be virtual functions. Yeah, that's why I'd left them out on this exercise. So part 3, when it starts looking at virtual functions and has you add the override keyword, whereas you can't, yeah, you can only use override when it's overriding a virtual function. That's what it is. Yeah, there was a reason I left it off. Oh, I haven't made my element 3D inherit from element, so I shall add that in there as well. Yeah, so we've got our area function here, which is going to return 0 for here. For now, I'm just going to copy that because the signature is very similar. And then, but for our 3D elements, we don't want to compute the area. Instead, we want to compute the surface area. So this way we can share functionality from elements, but then where they're branching at 2D and element, 2D and 3D, we can then change it. And then this one's going to be our volume. And again, these are all return 0 because we're going to override them later. So then once we've got those elements set up, we can go into our tetrahedron class. Actually, we should start with our triangle class. That would be a bad place to start. So we want to be able to construct a triangle from 3 vertices. So I'm just going to copy that over just to speed things up. So we can pass in 3 vertices, v1, v2, v3. And then we will call the element 2D constructor, and we'll construct our kind of vector of these vertices. And we should inherit from element 2D, so we can call that constructor. But we need to make that public. And also, because we're in a class, our default access is going to be private, so let's again add public to there. We can override our get num vertices function, because this is going to return 3, because it's a triangle. It's got 3 vertices, 3 corners. And then lastly, we can implement our area function. So this is going to return a double. And we have our formula for the area of a triangle here. So first we're going to construct our vectors. So AB is going to be, we can access vertices from element because of our inheritance. So we can get the first and second vertice and construct a vector AB for them. And then we can construct AC, which is going to be the 0th to the second. And then what we want to return is AB crossed with AC as per our formula up here. Then get the magnitude and then divide it by 2. I'm using 2.0 here to make sure we get a double back, not an integer. Division. So that is our triangle class completed. And then we just need to do similar for our tetrahedron. So the first thing we're going to do this time inherit from element 3D. Why did we not use vertices for defining a triangle? So we could have passed in a vector of vertices. The reason I haven't here is because we know a triangle is made from 3 vertices. It's whereas a vector can be any length. This is just some way so that when someone is using your class and constructing a triangle, they can't accidentally pass in 5 vertices and try and make a triangle from it. They have to pass in 3 individual ones. So we don't need to auto variable called area and then return it. Oh yes, yeah. So you could have some double area that you then return like that. But you don't have to. We can just do it. We can just put it in the return statement. When it gets compiled, it's almost certainly going to do exactly the same thing. Style-wise, I think I like doing that. But if this statement was like going to be really long, like having intermediate variables is probably a good idea. But something like this is fine. Yeah. Okay, so constructing a tetrahedron from 4 vertices. I'm going to copy this because it's quite similar. Just change the name and then add a new vertex. So this time we are saying we have to construct from 4 vertices. And again, we're going to pass it into call our element 3D constructor and construct our vector of 4 vertices here. Again, I'll copy because it's quite similar. We've got our get num vertices function. This time I'm going to override it. I'm just going to return 4. And then we're going to do our surface area. is going to return a double. It's another const function. And what we're actually going to do here, I'm going to copy it because it's a little bit of typing. We're going to use the triangle class. So a tetrahedron is made up of 4 triangular faces. It's got 4 vertices. They come together to form a kind of triangular-based pyramid, but it doesn't have to be regular. And so what we can do is we construct our 4 triangles. So if we have vertices A, B, C, and D, we've got ABC, ABD, ACD, and BCD. And we can just use our vertices arrays that we've got here in order to construct them, which then means our return statement can just be abc.area plus abd.area plus acd.area plus bcd.area. And we just add those all up, and we've already got that functionality done. So that will return our surface area. And then for our volume, again, we've got this formula here. So again, for time, I will just copy these over. So we can define our vectors AB, AC, and AD. So go from vertex 0 up to 1, 2, and 3 respectively. And then we can return using just this formula as we've got above here. So it's AB dot cross AC dot AD. So that at this point is we're going to return a double, and we'll just divide it by 6 to get the area of a tetrahedron. I mean, if you want to look up that formula and stuff, it is there to, if you are interested, but that is just, yeah, that's the formula of a tetrahedron. So we've got that all done. We'll do a make, although I haven't actually updated my main function. There are probably a couple too many steps to this exercise, I think, for the time we have available. So I'm just going to copy. So I've got some functions here that I didn't make my tetrahedron. I didn't add my public accessor to that. So I've got some functions here that just take in a triangle and a tetrahedron and do all the printing kind of that we've asked you to do here. You'll be able to find these solutions and look in more detail if you are wanting to, but we're just going to create a triangle, create a tetrahedron, and do the printing. Cool. And then we can look at our vertices and call all these functions, and we're seeing they're using our some of this is kind of inherited functionality, some of it is function that's defined directly inside tetrahedron or inside triangle. So kind of, yeah, if once you run this and if you ever go yourself, have a think about like what bits of functionality are being defined where, for example. James, do we have time to go through part 2 and part 3 as well? This is kind of the bulk of things, or do you want to move on to the next lecture?
I would like to get the next lecture in before lunch, just to keep us on track of time. I think we've got time at the end of today to go through some detail if people want us to discuss them. There are solutions on the GitHub as well, so it's not like there aren't parts of this that people can go look at.
Yeah, okay. I think next lecture sounds sensible. Cool. I'll stop sharing.
Okay, let me just give you 1 second. Okay, so we've now been through a lot of quite of the gory functionality of C++. And this is the bit where we try and convince you that all the pain and suffering is kind of worth it, and it's all nice from here on. It's never going to be strictly true, but what we're now going to start to discuss is some of the functionality within the standard library around algorithms that really enables us to take advantage of a lot of the detailed constructs we've done, especially around some of the iterators that we've developed. thinking about the Morton ordering example, and I'll highlight that as we go through this, especially that step 2 of the example where we've introduced an iterator. I say, before we get into that detail, let's start by introducing what we mean by algorithms. So when we've looked at iterating through containers or elements of arrays before, we've had these 3 kind of styles we've discussed. We've had the classic sort of C style where we iterate over some range, and we have to be careful about setting our limits carefully. We can do older style C++, where we explicitly state the beginning and end of the iterator and then increment the iterator to go work through a particular set of elements, or we'd use a range-based for loop. Okay. But ultimately, when we do this, we're implementing, these are all double in place examples, right? That just like take the value, multiply it by 2, dereference the iterator and multiply it by 2, get the item by reference and then multiply it by 2. The issue here is that we're having to manually define the actual update or the algorithm that's inside the for loop. Inside the iterator and inside the looping construct. So this is the looping construct, and then whatever's inside the bulk of it is then doing some operation on the data we're interested in adapting. A lot of these patterns are very common. You tend not to come up for the vast majority of the time anything particularly exceedingly exciting, unless it's incorrect. So it would be really nice if the standard library helped you have a lot of the defaults implemented for you, because then you can let the standard library implementers handle how to do this efficiently on different hardware, and then different compiler organizations can really hone this for a given hardware target. And you, as the person implementing and using this, is then abstracted away for some of the sort of nastiness of the way we're doing loops or the way we're using iterators and things like this. So there is the standard algorithms library that exists inside C++. It contains around 100 function templates that implement algorithms like count the elements that match criteria, or divide the elements based on a condition. These use iterators to specify the data that they will work on. So count, for example, might use the begin and end iterators to know where to start and finish operating. But they allow you to then access any container that allows an iterator and then do the algorithm count on the elements within that particular container. That's really nice. I don't need to go through trying to work out how I'm going to accumulate something or count something or do other weird algorithms. If I've already got vector, I don't need to like go in, access each element of vector individually, go get its value, count how many there are, things like this. I don't really want to be doing. Because it's very, very standard thing to do. So these things exist, and here we have a simple example. We have count the number of zeros. We've got the standard count algorithm that's stored in the include algorithm header. We've got some data that assuming we've read in somewhere, which is just a standard vector of ints. And we start at begin, we end at data.end, and we count zeros. And we go through counting until we've counted everything up. We could come up with some other operation, is prime, that we use then to count if some conditions met. So we haven't defined what this condition is here. I've just said there's going to exist some condition to say is something a prime number. And again, we can work through a list, a vector of data, and analyze whether there are prime numbers within this list. And then based on whether is prime returns true or false, this will be counted or not. To give you just understanding of a little bit what the guts here is actually happening is we require, especially in the COUNTIF example, we've got this example implementation. Now, this is not exactly how it's implemented in the standard library, but to kind of get you a sense of what's actually happening under the hood here, we have some template which says we can take any input iterator, and we have something called a unitary predicate. This is any unary is meaning one argument and predicate meaning Boolean valued function, which means it's a function which takes a single argument and returns a bool, a true or false, when it is run. So here we take an input, the start of our container via an input iterator and the end of our container via an output iterator. And we have some unary predicate, which is some way of testing whether we meet some condition. Inside this, we loop over from the beginning. But we assume we start at the beginning and then we iterate all the way till the end, till we met end, and then we increment first, so we iterate through the loop. We run our unary predicate, our test function, on elements of our container, dereferencing them first, check if their conditions met. So if this returns true, then we do incrementation. If we're doing count, for example, different algorithms have different things they do once they meet this condition. And then we return the answer of that count once we're done. But we're saving ourselves from all of this and having to write this ourselves if we use the standard library. And there's a whole host of algorithms that you can choose from. So simple things like for each element, which is obviously something we do all the time. Count if, as we've described. Find if. Returns the iterator to the first element matching the or end of if no match. So you might have used this when we were looking at some of the map examples a couple of days ago. There's copy, which we've experienced as well, and copy if. Okay, so just to go back a second, there's a question around why aren't we explicit about the starting iterator loop with first? So here, well, there's a missing element. This is someone being efficient and cheeky and probably should not do this in this example because it makes it confusing. There's the assumption that you are going to increment first. So because you have first here, if you have not got a starting position, you're always going to be dereferencing this element. Therefore, to begin with, it is the first one. We don't need to specify it's going to be the first, and then we will increment it. And the only thing we need is a condition to know when we've hit the last to stop doing this section of the loop. That's why we get away with that. It's questionable. It's fine for the compiler. It's questionable for the programmer. Because that's, if it's confusing, then it's probably not great programming. Okay. The point of this really is to say this is the type of thing that's happening under the hood. This is not exactly what's happening. This is just meant to be you will get to avoid all this fun and therefore make your code cleaner because you don't have to have a library of these functions around. Okay, so we have things like copy and copy if. We have things like transform, and able to take a function, apply a function to input elements and storing in some destination so we can transform data. Swap to values, we can do sorting, and we can do lower and upper bounds checking, these type of things. So all sort of very standard is another word that becomes overused here, but common functionality. And luckily the standard library defines it for us. So let's look at a couple of these. So for each, apply a function to every element in the range. So we have a unary function here called f, for every element within a range. And then again, we put the first and the last iterator of some container, and then we iterate it over applying the function. Why bother with this? It's much clearer about intent. Instead of me writing a for loop that then I have to determine what we're doing, because that for loop, just because it's a for loop, doesn't say we're making a change to every single element. I could have some weird offset logic, which meant that I was striding in there that would make it not very clear. This removes the chance you might have an off by one error because we're using iterators and we're going to check on the mask, so we can never skip elements and things like this unintentionally. This works very well with other range-based algorithms. It's very concise if your function is already is what your operation. This function is already defined somewhere else. That said, you may prefer a range-based for loop because in this case, in this particular case, but something like transform, well, we want to take multiple we want to provide an output destination might provide us a lot of very powerful functionality. So we have some input that starts first and ends at last, and then we only need the output first position of the container because it has to have the same number of elements as the input, because we're going to do a operation on each element, and then we're going to put that in the output. So here, this example below is again our double in place looks like. So we've got some data source, which is from some location. I've assumed that get data is defined well somewhere else. And I transform this data and double it in place by the input to the data is at beginning and the end of data is at the last position. The output is then again at the beginning of data. And then I have some function which will do the multiplying 2 that's defined somewhere else. So again, you can use your input as your output, but you don't have to. And the double in place functionality is stored in a function, and that allows us to make it very obvious what our intent is. And now a complex multi-line for loop that doesn't have to be, this operation is a simple example, but it could be a lot more complex, is now a single line. And it's very clear our intent is to transform some data, which makes it much easier for someone else coming along to get at why you're doing what you're doing. Okay. So some more motivation. So the implementations of these algorithms have been tested by your compiler authors. The library may be able to do platform-specific optimizations that you probably don't want to maintain in your own codes. You absolutely do not want to maintain these in your own codes unless you're doing very high-performance library development. You should avoid this if you can. And then are you really going to be, in some sense, that is not a challenge, okay? People often think that's some form of challenge to their ability to program. It is not. It is to say simply that often the hardware developers and producers provide you the most performant implementations. You should use them. They know all about the secret sauce that you can't see, basically. These also form a nice language to communicate with other programmers what the code is really doing. Basically, if I want to, I can remove, in this example here, if I want to have some form of copy, I could have a, do this, say, I could have a iterator from the beginning to an end, to start at some location and iterate until it's the end and increment it. If whatever thing contains, if the item in the container that the iterator is attached to contains a cat, I have some function contains cat that checks that, and then I'm going to push it back onto my directory of cat pictures, whatever. That's several lines of code. It's not very obvious what I'm intending. However, if I use the standard copy if, which is all I'm actually doing, it's very obvious what I'm intending by the name. I start images, end images. I have some container that contains all my cats that I want to say if it can, function that says, does this contain a cat image? And then I insert this result onto my output, which is catpics. Okay, it's just much cleaner. Okay. So now we've got a way of using and generating some transformations. What I've not really talked about, and those transformations can take some arbitrary functions that allow me to define myself how I want to do these transformations, or what transformations to do, instead of how they're applied on a particular container. I want some way to define those functions in a sensible way. And now to do that, we're going to turn to Lambda functions. Yeah, so all these algorithms need, or many of these algorithms need to provide a function like object as an argument to them. If you have to declare a new function for one-off use in an algorithm call, that's kind of inconvenient. So you and then the code may end up looking quite messy because you probably don't want to put that in some form of utilities directory because it'll get lost. Sorry, utilities header, that will get lost or get confusing because it moves code away from where it's used, or you've got to create some custom function object each time. That's not great. So what we'd probably like to do instead is have something that's a bit closer. So let's take this example here where we're trying to do this square out a constant type functionality and use it in some form of transformation. So I've got some function that's square out a constant, which is what I've defined, and I'm going to pass some vector in, and I'm going to pass the constant in, and it's going to return this updated vector with an answer. To do that, I'm actually going to call standard transform, and it's going to take my input at the start point and give it the input's endpoint. It's going to have the answer location, which is this new vector, which we're going to resize to make sure it's the same as our input, because we've got the same number of elements output after this transformation. And then we're going to have to provide some square and add constant function to do this operation. I need this object to have some form of, it needs to be able to be called by having some curly braces on it. So not curly braces, some standard brackets on it. But here I want to be able to pass in something, some constants defined as well. I need them to have some state. And what I end up actually doing is creating a whole class or structure just to do this. So I create some object with a constructor which takes my constant in, stores it as a data member, and then has a operator overload for the normal bracket operator, the function call operator, that then takes a float. And this float is going to be every single element of my input vector x. That's going to do the doubling by multiplying by itself, and it's going to add some constant which I've passed in. And this is quite verbose. I don't really want all of this just to do something simple like doubling, placing and add a constant. Okay, and to use this sort of transformation type operation. So we can use lambdas to kind of solve this problem. A lambda function, also called a closure, is a function object that does not have a name like the functions you have seen so far. You can define one inside a function body. You can bind them to a variable. You can call them and pass them to other functions. They can capture local variables by value or by reference, and they have unique unknown types. So you don't have to. So you have to use auto or pass them straight to a template argument. So they're these kind of special types of functions that have some lifetime, and we could use them here to do the same problem. So it's a less verbose example. So here, instead of having a whole different structure created just to do this, I have a lambda. Okay, and I'm calling this function, this lambda func. It's a terrible name for this. I would call this something much better than this if I had a lot of these. It captures some variable in the local scope, so the float c by value. It has some argument to the function created, which is just a double z. And here's the full body of that. What it's going to do, it's going to multiply z together and add c to it. Now, in my transform, I just pass func in instead of adding a whole class. I can make this even less verbose. I don't even need to bind this lambda to a particular function. I can just pass it in. And now my transformation is a single line which adds the lambda explicitly in its definition, or in the call noise definition. This is very nice if I've got very small bits that I need this type of sort of callable function to be defined in place that I only ever want to define once. Obviously, if you had lots of these, use this all over the place, this functionality, it may be when it's duplicated, you may not want to have it recreated every time, but if it's for one-offs, then this is really quite nice. It keeps the intent near where it's executed. Okay, so we've introduced some new syntax here, so let's just review that again. We have the square bracket that captures. This is the new syntax that indicates that this is a lambda expression, and it captures more ones, comma separated elements from the local scope. So that means that if you capture by some value, it's going to be whatever the value was in this local area. It has an argument list, and these are the arguments that are passed to it when the function is called. The lambda function is called. We have a function body, is what the function actually does. We have some return type where we can explicitly tell it what it's expecting to return, because the lambda hasn't got it's just going to be stored in a variable potentially or not. We can explicitly tell the compiler what we expect to be output by the function. And then as I was mentioning about captures, you can capture by value, making a copy. Or we can capture by reference. So we might do, say, if a variable is captured, there's a local variable was going to capture by value, but is put in that variable's name. If we want to capture by reference, then we need to put an ampersand to when we do the capture. There are some global capturing logic as well that we won't go into that has some risks associated with it. But these are things to really think about how you capture and what data you're capturing. So this creates a function object. Yep. Okay. So in the example here, there's an expectation that function takes no arguments. So here, we need a function that takes a single argument in that's going to be called within transform. Transform expects this to be something that has a function call operator that takes a single argument. That's what we're trying to do. When we looked at this here, this is calling the constructor. Here is the case where that is satisfied. There is a function call operator with a single argument. Okay. So we're trying to provide this. This may seem a little bit restricted for this particular case, as in, well, this is a lot of machinery just to make my transform call nice. There's other useful cases where you could use lambdas, but this is a nice example of where we can use it here. Okay. Yeah, so we can call this like any object that overloads the standard function call operator. So here we could define this, bind it to something called func, and then we could just call it like this, and this could be a lambda. Because it doesn't have a name, it cannot take part in overload resolution, so you need to be careful about that. It's not going to get. It is the lambda is bound to the variable function, variable called function. It is not a function with a particular name. It's a bit hard to get your head around, but when you play around it will become a bit clear. Okay, so quick question for everyone. Chat, what does this do? Yes, Isaac, we'll come on to that in a second. No one want to hazard a guess what this particular little bit of syntax does here? Okay. Does nothing. These three define a lambda. This thing calls it. So it captures nothing. It has no arguments. Body of the function doesn't do anything. And then it is called. Therefore, it does nothing. But that's valid syntax. The only thing isn't here is a template. There's the brackets for templating, but let's not try and make things otherwise even worse. Okay. So there's some different uses for this. So like we've seen, we might want to pass one small off piece of code in freely. So here we might have the sort algorithm. Or we have some molecules and we want to provide in a method for determining if something is larger than another. So molecules might have a number of different elements, which are going to be moles, and they may have data members which are charges, and you may want to be sorting them based on the charges. So you can use this to look at every single pairs of elements in molecules, neighbors, or elements, depending on the sorting algorithm. You compare. All you really need is a comparison operation, and we're just saying we can arbitrarily determine how that comparison operation is done. You may have a different sort on the same elements. We say, oh, I don't care about charges anymore. I care about mass or something like this, or chain length, or whatever your particular use case has. You can then define this when you come to use it. Again, keeping the details of what's being compared when it is near where it's called, which means this doesn't have to be a separate comparison operation to find somewhere else in the program. There's no need for that one. This is so small and self-contained. The other case where you might want to use this is for complex initialization. Now, this const, I think we've said in the past that this could be now done with constant expression and the more modern calls in C++, but when this is another way you can do this type of thing. Effectively, I want something that is constant, so we can't change it. I've set to like random numbers would be a good example here, but I want this to be set and then never editable. So that's what const is doing, but I do need to calculate it initially. So the point here is that I'm initializing this value of rands. This is going to take a capture of some size. It's going to have no arguments, and it's going to return a vector of floats. So that means that this is going to be auto is going to resolve this, the return type. So there's going to be a constant standard vector of floats. That's great. That's going to be a constant vector of random numbers I might need that I never want to change during the run of this particular code. And then the body of my lambda has the answer, which is going to be of the size we've captured. And then I can go through and call some function which gets me a load of random numbers. I don't care what function that is. It will add elements to, or update the elements of answer to get me a different random number. It will return the value. And then explicitly, we call that function, that lambda. So we define the lambda in place. We instantly call it. There's no parameters to call, so there's no way this changes, and therefore it is, when we come to run it the first time, rands is initialized with some values, but it is constant itself. Okay. So coming on to think what Isaac was getting at a minute ago, if your lambda is used locally, including pass to algorithms captured by reference, this ensures there are no copies and ensures no changes to be propagated. And ensures changes can be propagated, so you can update in place type things. If you use your lambda elsewhere, especially if you return it, because you can bind it to a variable, so a lambda can be returned, captured by value. This means that the values that you want to associate with that lambda are carried by it. If you were to capture by reference and then return it, the reference would point to something in the scope of the function you've returned from. That function, that particular case ends. That cleans up all of its stuff it's referred to. Therefore, what you've got is a lambda that's still floating around that points at some data that's stored that's been cleaned up. And therefore, you get some undefined behavior. So if you're returning stuff, make sure you capture by value. If you're in the local scope, you can use capture by reference. Try to keep lambdas quite short. More than 10 lines, then you should think about moving to a function or a functor instead. But for small bits of code that allow you to keep locality, they're quite useful for you. Okay. So just to finish off before we go to lunch in a couple of minutes. Yeah, as Nathan says, the variables which you capture must be available in the current scope. So they must be available in the current set of curly braces which you're capturing from. Okay. So performance, we now want to say, right, we've now got 4 different ways to do iteration in C++. If we include C-style iteration as well, why do we have all these different things? Which one's the best? I don't want to deal with all this different things. I want to pick a style and stick to it. So I'm not going to go through the detail of this, but this is the little sort of benchmarky test which has all 4 and provides some data for this. And what we can see is if we compile with -0, we don't include optimizations. C-style is a bit quicker. Okay, and all the range-based and algorithmic ones and the iterator style ones are all about the same, really. There's a little bit of change about certain sizes, but actually they're pretty equivalent. If we turn optimizations on, however, actually as much of a muchness, the performance is retained between them. Certain decisions are changing a little bit between them, but it's not huge differences. Maybe you'd actually just favor range-based a large number of element sizes because it's slightly slower, but I don't think it's something that you should be really worrying about. So the point is that you can really take the advantage of the nice encapsulation you get and the sort of reduced complexity of these more compact algorithms without worrying too much about the impact on your performance. But it's not much cleaner, reduces code complexity, and makes it easier for other people who come along to understand your intent in what you're programming. Okay. So we're going to break for lunch now for an hour. When we come back, we're going to look at the algorithms exercise, and we'll take some time to look at this. I know we're slightly behind what we said the schedule will be in the morning, but we always leave a bit of time in the last day, and the last couple of exercises and lectures are relatively short, just because we know you'll all be slightly waning after 3 days of training, and also we want to give ourselves buffer to explain this stuff in detail. So we'll return at 1:30. We'll spend about half an hour looking at this. Yes, we'll share the solutions. The solutions are on exactly the same GitHub that you've been looking at. It's just on a different branch. There is a solutions branch you can look up. And they are all in the same exercise files, in the same sort of relative locations. There's just a solutions section to them. So yes, please take some time now to have lunch, and we'll return at 1:30. Thank you for this morning.